Hey everyone, and welcome to our explainer on data link protocols. Now, I want you to imagine something for a second. Picture a completely chaotic physical network link. You've got dozens of computers, right? And they're all trying to shout at each other at the exact same time over this noisy wire. You just have raw data bits flying absolutely everywhere. It would be a total unmitigated disaster. Well, that is exactly where the data link layer steps in to save the day. Think of it as the ultimate invisible traffic controller. It takes all that digital chaos and organizes it into a perfect, reliable symphony of communication. Today, we're going to demystify exactly how your devices actually manage to talk to each other without dropping a single bit of information. Oh, and by the way, if you're studying for your 0478 computer science exams, this is absolutely crucial stuff to understand.
Okay, so let's dive right in by locating exactly where this magic happens. We're talking about layer 2 of the famous OSI model. As you can see, it sits comfortably right above the physical layer. The physical layer is basically just your raw connections, the actual copper cables, the optical fibers, the wireless radio frequencies that are just blindly blasting out raw signals. But layer 2 brings the intelligence. It's totally responsible for packaging up and safely transferring blocks of data across a single link between two adjacent nodes in your network. And why do we need this intelligence? Well, because the real physical world is messy. A real physical link suffers from all sorts of issues: electromagnetic noise, interference, weird propagation delays. So we absolutely need a strict set of rules to handle that. And that is exactly what a data link protocol is. It's basically the law of the land governing the orderly exchange of data, making sure that despite all the chaos of the physical world, our data blocks arrive perfectly intact and error-free.
So, here's our agenda for today. We're going to cover 1. Line discipline, 2. Flow control, 3. Error control, 4. Transmission modes, and finally, 5. Sync versus async protocols. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's get into it.
Section 1. Line discipline. Who should send now? So, line discipline is all about determining exactly which device gets to transmit and which gets to receive at any given millisecond. You can really think of it as a bouncer at a busy club, making sure people don't collide at the door. And we've got two primary ways to do this. On the left side here, we have NQ/ACK, which stands for Enquiry and Acknowledgement. This is essentially peer-to-peer. It's like politely asking a friend, "Hey, are you ready?" before you throw them a ball. You send an enquiry, and if the receiver is good to go, it replies with a positive acknowledgement, an ACK. If it's busy, you get a NAIC, a negative acknowledgement. On the right, though, we have poll/select. This is for when you have one primary boss station and multiple secondary stations. It's literally like a teacher calling on students in a classroom. The primary device polls the secondary devices asking, "Got any data for me?" Or it selects them, basically saying, "Hey, get ready, I'm sending data your way."
Moving right along to Section 2, Flow Control. How much data may be sent?
Flow control is all about coordinating the speed of the transmission. You see, if you have a lightning-fast sender, you really don't want it to completely overwhelm a slower receiver, because that just leads to dropped packets and lost data. The most basic way to handle this is called stop and wait. It is literally exactly what it sounds like. The source sends one frame of data and then, boom, it just stops. It completely stops transmitting and sits there waiting for an AAC from the receiver before it even thinks about sending the next frame. As you can probably guess, with a massive time lapse between sending a frame and waiting for the reply, it's terribly inefficient. Most of the time, the network is just sitting idle.
To fix that glaring inefficiency, engineers came up with sliding window flow control. This is brilliant. Instead of stopping after every single frame, we set up these imaginary boxes or windows at both the source and the destination. This window allows multiple frames to be sent consecutively, and they're all tracked using a continuous modulo n numbering scheme. The window shrinks as you send frames out, and it expands back up as you receive bulk acknowledgments. What this means is we can keep that data pipeline totally full, massively improving how we utilize the network bandwidth.
Now, here's a really cool trick for two-way communication called piggybacking. Normally, sending a dedicated ACK frame back to the sender costs extra processing and adds extra headers. But with piggybacking, the acknowledgement gets a free ride. It just absorbs right into the header of a regular data frame that already happens to be heading back in the reverse direction anyway. It's an incredibly smart way to beautifully conserve our channel bandwidth.
All right, Section 3, Error Control. How can errors be corrected?
So no matter how perfectly we manage the flow, the real world is going to mess with our signals. Frames get damaged by electrical noise, or they just get lost entirely. We need a safety net. When errors are detected using mathematical checks, like a CRC or cyclic redundancy check, the system relies on something called ARQ. That's automatic repeat request. Basically, the moment a receiver detects a bad or corrupted frame, it automatically fires back an AAK. And that knack instantly triggers the sender to retransmit the lost or damaged data. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
But wait, how exactly do we retransmit when we're using that sliding window we just talked about, with multiple frames flying through the pipeline? We have 2 choices here. First is go back N. Let's say frame number 4 gets corrupted. With go back N, the system just dumps everything and forces a retransmission from frame 4 onward, even if frames 5 and 6 arrive perfectly fine. It's simple but kind of wasteful, right? The other option is selective reject, which is way smarter. It actually holds on to the good frames that arrived after the error, and it explicitly asks the sender to retransmit only that single bad frame.
Section 4. Transmission modes.
Okay, so now that our basic rules for discipline, flow, and errors are established, how do we actually group the alphanumeric data characters for the physical journey? Well, we have 2 distinct modes. In character mode, codes are sent asynchronously. Literally, the millisecond a user presses a key, that single character fires off to the destination. On the flip side, we have block mode. Here the characters are buffered up in memory first. Then when the user hits send, the whole assortment is blasted out as one cohesive block or frame. This is incredibly efficient and absolutely perfect for those multi-drop networks where we're constantly polling devices.
And finally, Section 5, Sync versus Async protocols.
Let's look at how all these concepts come to life in actual data link protocols. We generally categorize them into character-oriented and bit-oriented formats. Let's start with the older standard, character-oriented protocols. These guys interpret a frame of data as predefined fixed patterns, usually 8 bits each, that represent unique standard characters, like from the ASCII set. They rely heavily on specific control characters to direct traffic, like STX for start of text or ETX for end of text. Some classic examples of this include IBM's BiSync for half-duplex communication or the Kermit protocol used for simple file transfers on early PCs.
Conversely, we have bit-oriented protocols, or BOPs. These are way more modern and efficient. Instead of hunting for specific 8-bit text characters, these protocols just see the transmitted data as an opaque, continuous stream of individual bits. This means control info can just be a single bit rather than a whole byte. Because they aren't bogged down by a specific character set, they are vastly more efficient and let you pack way more payload into much shorter, tighter frames. To make this concrete, let's look at a classic asynchronous example, the X modem frame. You can clearly see all our traffic rules right here in action. It kicks off with a start of heading control character. Then, look at this. We have our sequence numbers, which we know are absolutely vital for sliding windows to prevent duplicate frames. After that is our fixed 128-byte data payload. And finally, holding up the rear, a dedicated CRC error checking tail to satisfy our error control needs.
Of course, as computers got faster, X modem had to evolve. People needed larger file transfers. So it evolved into Y modem, which multiplied its data payload capacity massively to 1024 bytes and added a stronger 16-bit CRC check. And eventually, that evolution led us to Z modem, which is a highly optimized protocol combining the absolute best features of both for incredibly fast, reliable transfers over those old telephone lines. And we definitely can't forget the heavy-duty enterprise side. In the 1970s, IBM developed Synchronous Data Link Control, or SDLC. This is a robust, synchronous, bit-oriented protocol designed to orchestrate massive mainframe networks over wide area networks. Instead of using start and stop characters, SDLC uses bit flags as wrappers to signify exactly where a frame begins and ends. This allowed it to flawlessly manage data over point-to-point or really complex loop topologies without dropping a single bit.
So what does this all mean for you? Well, these foundational protocols, from the early X modem to SDLC, literally pave the way for everything we do online today. They define the exact rules for line discipline, flow control, and error correction that our modern networks are entirely built upon.
So the next time you stream a movie or download a massive file without a single glitch, just ask yourself, what highly evolved, invisible traffic controllers are working flawlessly behind the scenes on your device right this second? Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.